Hi everyone, welcome back to Mr. Carroll's classroom. Today we're going to work on transforming trig functions. Alright, so today we're going to basically be showing the three trig functions out of the six, which are the sine, cosine, and the tangent. We are not going to show the secant, cosecant, or cotangent. Those are slightly more advanced, okay? So in the last episode, what we did was we went ahead and we learned how to graph the parent function of y is equal to the sine of x. And then we also graphed the parent function of y is equal to cosine x and also the parent function of the tangent of x. Okay, so this here in orange is what you're seeing, which is y is equal to the sine of x. And so today what we're going to be doing is transforming this thing by stretching and compressing both horizontally, vertically, and then flipping it, moving it, shifting it up, down, left, and right, those sorts of things. Okay? All right, so here we go. And one thing I do want to remind you is that when we graph these specific functions, these specific trig functions based off of the unit circle, remember, there are six trig functions, and what they're doing is they are each measuring a specific aspect of this unit circle, essentially, some kind of measurement based on this unit circle, okay? And what we're doing is we are plugging in an angle. So along our horizontal axis, we are going to plot what that angle is that we plugged in, starting at 0, the initial side, and then wrapping it around, all right, 360 degrees, and keep on going multiple cycles in the positive direction, and then also in the negative direction as well, okay? We can also go clockwise as well, okay? And what we're doing, what we're plotting in the vertical is going to be the result of plugging into that particular function. What you're seeing here is us, in the orange, is us plugging in an angle, which could be in degrees or radians. We typically like to use radians, but anyway, and then getting out whatever the sine of that angle is, okay? And the sine happens to be the y value, okay? The cosine looked like this, which is actually extremely similar to the sine. In fact, let me overlay the sine on this real quick, and you can actually see that these are the same exact graph. They're just shifted over from each other. In fact, they're pi over 2, or 90 degrees apart. Okay, and then we finally graphed the tangent, which is going to give you this interesting looking graph, and it has these vertical asymptotes because the tangent is defined as the sine divided by the cosine, and sometimes that cosine value is 0. And so when we divide by cosine, or sometimes we're going to have to divide by 0, which we can't do, right? So we get these undefined areas which create these vertical asymptotes. Okay? All right. So what I'm going to do now is we're going to head over actually to Desmos and just get a feel for what these are going to look like. Okay, and before we do that, I just want to reiterate, because I think it's extremely important, what we're actually measuring with these six trig functions. Okay, so if I have an angle, and that's the one thing that's missing from this particular graph here, but imagine I have this line going from the origin to the point on the circle. Okay, the angle between this initial side, the positive x-axis, and that line, that would be the angle that we're measuring. Okay, so what I want to say is that if I measured the sine of that angle, I would get the measurement of this blue segment right here. If I plugged in the cosine of that angle, I would get the measurement of the red segment. If I plugged in the tangent of that angle, I would get the measurement of this black segment. The cotangent is the green segment. The secant is this orange segment going across, and the cosecant is the length of this purple segment going in the vertical right here. And so as we rotate this angle around, obviously all of these are going to change, okay, but they're all extremely closely related to each other. In fact, remember, we have the sine and the cosine, but then tangent is really just another form of those two. The tangent is the sine divided by the cosine. The cotangent is the cosine divided by the sine. The cosecant is 1 divided by the sine. The secant is 1 divided by the cosine. So everything, the other 4 of the 6 trig functions are really based off of those original 2 of the sine and the cosine. Okay, so they are very closely related to each other. As one changes, the others will change. Okay? All right. next up, I'm going to isolate one of these. So as we rotate around, let me start this up. We're interested in graphing just one of those trig functions, okay? So here you can see along the horizontal axis, I'm using radians. So we're starting at 0, then we're going to pi over 2, then pi, then 3 pi over 2, and then 2 pi, and then of course everything in between, but those in between numbers are, you know, we know the overall shape of the graph, so we're just gonna kind of do our best to fill those in, okay? So there's what the sign looks like, right? For example, as if I plugged in the sine of pi over 2, I would get 1. And so that's why this is getting plotted at point pi over 2 and then 1. Okay? If I plugged in 3 pi over 2, sine of 3 pi over 2, I would get negative 1, which is why the graph dips down here. And if I went ahead and stopped this thing, and you could see that was one cycle, but really it goes on forever in the right direction and forever in the left direction. Okay, and I can of course layer on top of this let's go ahead and put on the cosine. So here's the cosine. Just kind of start this thing off. Okay, which this is the red measurement, right? Which is that horizontal measurement. Okay, and I'm going to turn off the cosine. Let's go ahead and see the tangent very quickly. So now you can see that, you know, where are we getting this crazy tangents measurement here with the vertical asymptotes. Remember, that's sine divided by the cosine at whatever particular angle we are looking at. And then, even though we're not going to actually graph these today, take a look at the secant. So here's what the secant looks like. Kind of interesting. Remember, the secant is 1 divided by the cosine. And let's do the cosecant, which is 1 divided by the sine. Another, you know, fairly interesting as well. And then finally, let's do the cotangents, which is going to be cosine divided by the sine. Looks fairly similar to the tangent. Okay. All right. Anyway, so these are what the 6 trig functions all look like. And if you're kind of curious, let's just plot them all on here all at once. And you can see what all of these look like. They're all related to each other. And let me just stop this from, whoops. There we go. So you can see now these are all going on to infinity, all in their respective colors. So kind of crazy, but they are all completely related. And they really all start with that sine and cosine right here. Okay. Okay, so let's go ahead, and what we're going to do now is we're just going to start manipulating y is equal to the sine of x. So what I have here in the upper left-hand corner is y is equal to a times the sine of b times x minus h, and then all plus k. So let's start with the outsides, because these transformations, if you know anything about transformations for other functions, these are actually the exact same transformations. The outside is going to affect the graph vertically. Okay, so the plus k is going to shift this thing up and down. So if I change k, if I move it up, right? If it's like 2, it's going to go up 2. If it goes down, it's going to move the whole thing down. Okay, so that's what k does. I'm going to reset it back to its original starting point at 0. The A value out front is very interesting. It also affects it vertically, and it's going to be a vertical stretch or compression. So as it increases, it's going to be stretched out. Okay, and actually this measures the amplitude, which I'll talk about in a second. And as this thing compresses, meaning it goes into decimals, like for example 0.6, 0.5, 1/2, whatever, it starts to compress, and then it hits 0. So it's a flat line, because 0 times anything is just 0. And then once it's negative, it actually gets flipped or reflected over the x-axis, and it starts stretching in the other way. So you can see as A changes from positive to negative, how this graph is being affected. Notice the A does not affect the period at all. This period, the period is the amount of time it takes to go through one cycle. And so basically if we start at 0, you get all the way over here, which just happens to be 2 pi. And notice that 2 pi, that does not change at all when I change A. Okay, it just changes the max and mins of this, or what we would call the amplitude. All right, let me reset the A to 1. All right. Next up is going to be the inside. All right, so let's talk about these. The H is the same thing that you guys are used to, which is going to be a horizontal shift left and right. It's always going to be the opposite. So if you saw like x minus 3, it's actually going to go right 3, or x plus 3 is going to go left 3. But anyway, so you can see this is simply a shift in the left or right direction. The one thing worth noting here is that for I'm not really sure why actually, but we typically don't refer to like for all of the functions we refer to this as a horizontal shift, but for trig functions we call it a phase shift. Okay, it's just another name, but that's what we typically call it, a phase shift. Okay, and then there's B. Now B is going to be represent a horizontal stretch or compression, and it is also the opposite. So as B increases, it's actually going to be horizontally compressed, and as B decreases, as far as fractions go, it starts getting into fractions, it's actually going to elongate. So this is actually going to change the period, all right, how long it takes for this to go through one cycle. So let's go ahead and change B a little bit. Let's increase B. So you can see as B increases, it's going to compress horizontally, and so the period is going to get smaller and smaller and smaller. For example, right here, this is about a period of 1. Starting at 0, going up, down, and then about 1 would be the period when we repeat. Okay, let's go down now. So as B decreases, it starts to get longer, and the period starts to get longer. And then, of course, you can, this thing can get very, very long, by the way. If B is 0, of course, it's going to flatline here. But then if B is negative, then it is going to reflect over the y axis, in this case, the vertical axis. Okay, it has the exact same properties. So there you go. All right, so let's go ahead and we're going to go back now to our working area. And what I want to do is show you the kind of, I guess it'll look a little bit complicated, but here's what everything that I literally just talked about. Okay, so over here, I have my, transformation form, whatever you want to call it, of the sine function. And the only reason why I'm doing sine here, by the way, is because it doesn't really matter. It's going to be the same for cosine. And the tangent is slightly different, but it still has the exact same properties. But anyway, so the A here is going to be your vertical stretch or vertical flip, or which you could say reflected over the x-axis. The K on the outside is your vertical shift, up or down. On the inside, we have H, which is our horizontal shift or our phase shift. That's what we typically use, this word phase shift. And then B is going to be our horizontal stretch or horizontal flip, or you could say reflected over the y-axis. All right, so a couple of things worth noting is that we can actually measure certain things based on these values. So for example, down here I have the amplitude. The amplitude, which basically tells you from the midline here, from the midline going going up to the max, or the midline going down to the min. That's our amplitude. Okay, that's what it means to be the amplitude. Okay, so the amplitude is the absolute value of A. The reason why it's the absolute value of A is because this is a measure of length, and so we don't use negatives here. Okay, let's see here. The B can be used because remember the B is what changes this period. The B can be used, at least for the sine and the cosine, to measure the period. It turns out that you can take 2 pi divided by b, and that will be the period of the sine and the cosine. Now the tangent is half of that, so it's pi over b for the tangent if you want to measure the tangent's period. Okay. And then finally, the K on the outside, this thing, how far it gets shifted in the up direction or the down direction will determine its midline, the line that goes through the center of this thing. So you can just say the midline is just y is equal to K. All right, so with all that knowledge, what we're going to do is we're going to graph 4 problems. And so let me bring those up over here. So the 4 problems are going to be, let me get this out of the way. The 4 problems are going to be y is equal to 2 times the sine of x, y is equal to negative 1/2 times the cosine of theta plus 1. And by the way, x, theta, z, whatever. It doesn't matter. You can name these variables whatever you want, but we know that what we're plugging in is the angle, okay? Anyway, the next one, the third one is going to be the sine of 2x, and then the last one is going to be the tangent of theta over 2. Okay, so this basically represents all of our different transformations except for the phase shift, or that h. So that is something that we're not going to do during this video. It's slightly more advanced. Okay, and really it is just moving it left and right. The only reason why it's a little bit more difficult is because, or typically more difficult, is because our scale in the horizontal is usually not just 1, 2, 3, 4. We're using like pi over 2 and pi and 3 pi over 2. So it makes it a little bit more difficult to calculate those shifts. Okay. All right. So let's go ahead and we are going to get started. And one thing I want to note is that I am going to attempt to use the same scale for all of these problems. The first step to pretty much graphing all trig functions is to figure out the period, because once you figure out the period, then you can go out, like for example, this period for 2 times the sine of x, this period is 2 pi divided by b, which in this case b is 1. There's a 1 times x here, right? So 2 pi divided by 1, which is equal to 2 pi. So once I figure out that period, I will then go out and label my x-axis, okay, or my horizontal axis. So I'm going to go out to 2 pi, and then I divide it into fourths. Why? Because let's take a look at our unit circle. Our unit circle, we start at 0, and then we go all the way around to 360, right? And we've gone through one cycle, right? And you could say to 360 or to 2 pi, whichever you're using. But how is this split up? Well, it's split up into fourths, right? So here's your first fourth, here's your second fourth, here's your third fourth, and then did I say third fourth? And then here's your fourth fourth, right? So so that's why we do that. We typically go ahead and label one cycle, and then we split it up into 4 because it's easy for us to figure out this point, this point, this point, and this point. Okay, so let's go back. All right, and let's go ahead and start graphing this thing. All right, the way I'm gonna graph these, because there are really a couple ways of doing this. You could plug and chug, right, where you actually like plug in the values in your calculator and figure out what they are. I'm not doing it that way. What I'm gonna do is I'm going to use my knowledge of knowing what the parent function looks like, and then I'm gonna shift it or transform it based on whatever transformations are taking place. So for example, I know that the parent function of the sine actually looks like this, right? It starts at 0, pi over 2, it goes up to 1, pi goes back to 0, at 3 pi over 2, it goes to -1, and then it goes back to 2 pi. And then it just repeats over and over and over again in both directions. So how is this going to change based on the transformations here? What are the transformations being taken place? Well, in this case, it's just a that's changing. Instead of a being 1, it's now 2. And so what does that do? Well, that is going to vertically stretch this by 2. Okay, so let's go ahead and show what that means. So basically, that means that 0 times 2 is still 0, right? But here at 1, it's not going to be 1 anymore. It's going to be 2 times 1, which this is going to get moved up to here. So it's going to go up to here and then go back down to 0, because 0 times 2 is just 0. And then at -1, it's going to go be -1 times 2. So it's just going to get stretched to -2, and then it's going to go back to 0. Okay, so let me erase all this, and let's just go ahead and put in our final graph. So 0, 0, and then at pi over 2, it's going to go up to 2. And then at pi, it's going to go back to 0. And then 3 pi over 2, it's going to go to -2. And then at 2 pi, it is going to go back to 0. And so I'm going to go ahead and fill this in as best I can. That looks not too good, but it's okay. All right. And so, again, what I would say here is that this is pretty much the same as the parent function, except the amplitude, which is the absolute value of a, is going to be 2 instead of 1. So the amplitude is the distance from the midline, which is the line that goes straight through this, the heart of this function, from the midline up to the max, and then the midline down to the min. Okay, so let me get rid of those notes, and then I am going to go ahead and just complete this. Okay, that is one cycle, so the period of this is 2 pi, and let's go ahead and just finish this off, because it's going to go on forever. And I'm going to use dotted lines just to show you guys, you know, that this is a new cycle. And I'm going to do the same thing here as well. Okay, and so there we go. So there is the graph of y is equal to 2 times the sine of x. All right, let's move on to the next one. All right, so this next one is actually fairly complicated because it has quite a few transformations, which is why I wanted to throw it in there. Okay, not only is the amplitude going to be 1/2 instead of 1, but this is going to get shifted up by 1. So the midline, instead of being right here going across at y is equal to 0, it's going to be y is equal to 1, which I'm actually going to plot that. And then finally, this negative in front is actually going to vertically flip this thing or reflect it over the x-axis, okay? So I'm going to do this in steps. The first step is going to be, let's just remind ourselves what the cosine, the parent function, looks like. At 0, the cosine is 1. At pi over 2, it's 0. At pi, it's -1. And then 3 pi over 2, it's 0. And 2 pi, it goes back to 1. And then this would be 1 full cycle of the cosine function. Okay, kind of has that horseshoe look to it. Of course, it would then go on, you know, in forever in both directions, and it looks a lot like just like the sine function. All right, but anyway, so how is this going to change? Well, first of all, it's going to go up by 1. Actually, let's shift it. We'll kind of shift it afterwards. Let's actually do this negative first. Right, so it's going to get flipped vertically. So it's actually going to look like this. Okay, then it's going to get compressed by 1/2, so it's really going to be like this. And then it's going to get shifted up by 1, so every point gets moved up by 1, so it's actually, I don't even know if I can do this at this point, it's going to look like, kind of like this, okay? So let's go ahead and make these changes, okay? So here we go. So here is these original points. And so I'm just going to basically just change these points, okay? And so let's do the vertical flip first. So I'm going to say these are all going to get reflected over the x-axis. So I'm going to take away these points. And so instead of it being 1, starting at 1, it's going to start at -1, and then go to 0, and then go up to 1, and then 0, and then down to -1. So you can see here this is vertically flipped like that, okay? All right, next up, let's take care of the compression, so 1/2. So instead of it, the amplitude being 1, it's going to be 1/2. So instead of going down to -1, it's going to be here at -1/2. Instead of going up to 1, it's going to be at +1/2, and then same for this one, -1/2. So let's go ahead and put those in. So -1/2, still 0, +1/2, still 0, and then -1/2. All right. And then the last thing we need to do is we need to shift everything up by 1. So instead of -1/2, this whole thing is going to get moved up to 1. Instead of 0, it's going to be 1. Instead of 1/2, it's going to be 1 and 1/2. And then this gets moved up to 1, and this one gets moved up to +1/2. Okay. So now that I have all of those, I'm actually going to just erase these other ones. Okay, and I am going to also go ahead and put in this midline. Let's see if I can draw a decent midline here. It's really pretty bad, but that's okay. But anyway, so here we go. And let me actually just extend this a little bit more because I want it to go past when I connect all these. Okay. Okay, anyway, so there we go. So that's our final final transformation. So I'm going to go ahead and connect these. Okay, there we go. And so I am now going to go ahead and put in the rest of these points. Okay, so this one's going to go back up to 1/2. Just follow the pattern here, right? And then this one goes up to 1 and 1/2. And then this one here is going to go there up to 1 and then 1 and 1/2. Okay, there we go. So yeah, that was a pretty tough. That was a pretty tough one, right? So we have a vertical shift, we have a vertical compression, and then we also have a reflection over the x-axis, or a vertical flip. Many times I call it. And there we go. So let's move on to the next one. Okay, so this one here is our first one where we have this B value. Okay, now the B value is going to be really important because this is going to change our period. So the period, and this is the sine, by the way. This the parent function of sine has a period of 2 pi. So this is going to change. So remember our formula here that the period, I can draw this right next to this if I have room. Yeah, there we go. Period is equal to 2 pi over b, which is, in this case, 2 pi divided by 2, which I'm going to run into my head here, which is equal to, 2 pi divided by 2 is pi. I almost wrote down 1. But anyway, so there we go. So the period here is going to be pi in this case, okay? And so, sorry, I'm going to move back over here so you guys can't see that. So let's go ahead and graph this thing, because really there's nothing else that's changing. Remember, the original sine goes from here to here, here to here, and back there, like that. And so all that's going to change now is that this is going to get squished in, right? Instead of having a period of going from 0 to 2 pi, it's going to be 0 to pi, okay? So let's go ahead and change that. So I'm going to go ahead and just put in like some little markers here. And so this is actually going to be pi, if you guys can see this, pi over 4. And this one is going to be 3 pi over 4, right? 0.75 of pi. And so let's go ahead and put in our points. So again, it still goes up to 1. The amplitude is still 1, right? We still have a 1 in front of here. It's just really just the period that's changing. So we go back down to 0, right? Go to -1 at 3 pi over 4, and then we go back to 0 here. So there we go. So let's go ahead and connect the dots. And there we go. There's one cycle. Let's go ahead and create another cycle. So halfway between. And I'll put in a little dotted line here. And I'm not going to do it all the way, but these are, of course, are going to go forever. Yeah, I'll just do one of those. Do a half of a cycle. Okay, anyway, there you go. So there is going to be the graph of sine is equal to, the sine of 2x. All right, and let me go ahead and erase this work here just so it's not in the way of our next one. All right, so let's go ahead and remove this whole thing, and we're going to go to our last one, which is going to be f of theta. Just switched over from x to theta, just because why not? So f of theta is equal to tangent of theta over 2. So again, there's really only one thing that's changing here, and it's this b. All right, I don't know why I put a capital B, but it's this b here. So what is this b? It's actually 1/2 times theta if I moved that out from it. So b is 1/2. Now, one thing that you have to be really careful for is the sine and the cosine. If you're measuring the period, it's 2 pi over b, but for the tangent, it is pi over b. Okay, so pi over b is going to be pi divided by, in this case, b is 1/2. So now I'm dividing by a fraction. So how do you divide by a fraction? Well, you multiply by its reciprocal, right? So this is equal to pi times the reciprocal of 1/2, or 2 over 1. And so pi times 2 over 1 is equal to 2 pi. So this period is going to be 2 pi. Now, another thing you have to watch out for is that the tangent, it really straddles the origin, actually. So remember, let's just go ahead and mark our parent function for our tangent. So a tangent goes through 0, 0. It has a vertical asymptote right here, and another vertical asymptote at pi over 2, and another vertical asymptote at negative pi over 2. And then at halfway between, it goes down to -1, and halfway between, which by the way is 45 degrees, or pi over 4, is going up to +1. So it actually looks like this. And the period is going to be the distance, right, between negative pi over 2 and pi over 2, which is just pi. Now in this case, how are we changing this? Well, it is going to, the period is going to expand, right? This 1/2 is going to not compress it, but it's going to stretch it out to 2 pi instead of just pi. Okay, so basically I need to go out, instead of half a pi on each side, I need to go out by a pi on each side. So let's go ahead and do that. And again, I'm going to use the, I'm going to use the, just the idea of the parent function in order to assist me in graphing this. So here we go. So I'm going to go over by 1 pi this way and over by 1 pi that way to get a full length of 2 pi, all right, a full period of 2 pi, I should say. All right, so let's go ahead and we'll put down these asymptotes, vertical asymptotes. There we go. And halfway between here, so in this case at pi over 2, you are going to go ahead and get 1. And at negative pi over 2, you will get negative 1. And there we go. So let's go ahead and graph the rest of this. I'll connect the dots based on the shape that we know. And there we go. And so I can go ahead and do another one of these by going over 2 pi. Oops, trailing off there. And we'll go ahead and plot our points. 1, negative 1, and there we go. Okay, so graphing 2 full cycles. All right, and let me erase my work, because now what we're going to do, now that we've done all 4 of these problems, is we're going to bring all of them back up here. So problem number 1 was 2 times the sine of x. What did that do? It increased the amplitude to 2 instead of 1. Next one, we graphed y is equal to negative 1/2 times the cosine of theta plus 1. What transformations were made? Well, it moved up by 1. It got vertically compressed by 1/2, and it got vertically flipped as well, or reflected over the x-axis. I don't like to say reflected over the x-axis, and the reason why is because if I do the other transformations first and then I reflect it over the x-axis, like, shouldn't it be down there? So, you know, I know that's the common terminology. We say reflected over the x-axis, but I just like to say vertically flipped. But anyway. All right, so problem number 3 was this blue one here, the sine of 2x, which really all this did was compress the period, okay? And problem 4 was our tangents, and so in this case, it is the same as a tangent, except it's stretched out our period. All right, so there we go. All right, that looks like a giant mess on the screen right now, but those are 4 problems full of different transformations. The one transformation that we did not cover is that phase shift, which again, phase shift is not that complicated. It's just moving it left or right. The only real difference is that you're typically using, or you're dealing with radians in your scale, so it makes it a little bit more complicated to calculate those changes. Okay. All right, guys. So that's it for this lesson in transforming trig functions. You can go on if you want to try out the other 3 trig functions, which are the secant, cosecant, and cotangent. And other than that, the transformations are all going to work exactly the same. All right, guys. Hopefully you enjoyed this lesson, and I'll see you in the next one. Take it easy.